find the area, basically we're looking at our different rectangles and we're adding them together. Now, your total distance going from B to A here is B minus A, and we're dividing it into n rectangles. So the width of each rectangle is B minus A over n. Now, we really want to go ahead and figure out the total area here. We want to eliminate this blue stuff, which is basically the air. Well, to do that, we want to go ahead and add together all these rectangles, and that's what we have with this right here and this right here. The only difference is this one here is looking at the area below your curve, because that's why the bar is below. So that would be all the white ones here. This one here is looking at the area above your curve. That would be looking at the heights of all the rectangles that go from the bottom all the way up to the top of the blue. And that's adding your area underneath plus a little bit above, so then it's above. Now, for the most part, all we want to do is increase the number of rectangles that we have. If we do that, the area below your curve and the area above your curve will be equal. And so therefore your area is equal to what you get from your upper and your lower. And if you take your limit of that summation formula, we get this right here. That's our formula we're going to be using. You also need to be aware of these two formulas here. They're going to be very important, so make sure you have those written down. So we're going to start off here, going back to that problem that we estimated with our calculators, going from 0 to 3 of our x squared. Now, you're going to start off, your ending of your interval is always b. The beginning of your interval is always a, and it's always x naught. So we're going to use this first formula to be able to help us figure out our formula for delta x. So 0 is your a, 3 is your b. You simplify the top and you end up getting your formula. So delta x is given to you by this formula. Well, we need to go ahead and also figure out your x sub I. X sub I, once again, is the initial here, which is 0. And then you got to go ahead and plug in delta x. Well, delta x is what we just figured out over there in the lower left side here. Plug that in, we get this. So your x sub I simplifies down to just being this. Well, we're going to start off with our formula here, and I did not write the limit in each one of these in front of each sum. It technically should be there. We want to look at your function of x sub I. Well, your function is x squared, so basically you got to take your x sub I and square it, and that's what we have here. So now, what is x sub I? Well, let's just go ahead and plug that in. When we plug that in, we get this. Now we also have your delta x. Delta x, once again, is what we had right here, the 3 over n, and you plug it in, you get this. So now you square the top, square the bottom, we get this here. Now all you want to do is just go ahead and multiply your fractions together, multiply the top, multiply the bottom. Now, we have some constants here that we can pull out. So we're going to pull out our 27, and we're going to pull out the n cubed. N doesn't change. It's not our variable. It's going to be a constant. In this case, we're going to look at our limit as n gets really big and what happens with that. But for right now, you can think of it as a constant. So you end up pulling this out. You have this here. You did not do anything with the I squared, so that's still hanging out after your sum. Well, we now have a formula for the sum of an I squared. The formula for the sum of I squared is given to you over here. And so I'm going to replace the sum of I squared with this formula here, the second one. Typically, if you don't know the value of n, in this case we don't, you're going to always want to use the second formula. So you plug that in, and so then this is just the sum of I squared formula here. All we're going to do now is just basically get rid of the parentheses by distributing through. And we get this. Now we need to take the limit of that. Well, here, these two fractions have variables in the bottom. As n gets really big, they go to 0. So it's 9 plus 0, or 9 for the area. And you'll notice with what we did before, for figuring out estimating the area, your average of the left and the right, which was your trapezoid, was close to 9. So let's go ahead and take a look at a problem here. We look at the number of rectangles increasing, and you'll notice up here as I increase the rectangles, these values change, get closer and closer to the exact value. And we're looking at the left endpoints. You notice the white area underneath your curve is disappearing as the number of rectangles increases, and your left endpoint gets close to the exact value. Well, if we go back here, we could do that also with the right endpoint. And you'll see as the number of rectangles increases, the area becomes more accurate. And then we also have midpoint rectangles. With a midpoint rectangle, in the middle of the top of the rectangle is what really touches your curve. The whole idea is that this little triangle right here, almost triangle, is more or less the same as that triangle there, and it offsets it. They're not perfectly that way, that's why it's an estimate, but that's more or less what's going on when you think of the midpoint. And when you do the midpoint, you notice the midpoint is the most accurate of our three estimates. We can also come back here, not just go ahead and take a look at midpoint and change the number of rectangles, but we can actually change our curve. Now, if we just drop this down a little bit, you'll notice that your area now becomes negative. Why is your area negative? Because you actually have more area underneath your curve, underneath the x-axis, than you do above. And you can continue to move this around and get different shapes. And we could even change our function if we wanted to, rather than just sliding our function around. But hopefully that gives you a little bit better view of visually what's going on when we're looking at our Riemann sums.